Yeah, hello, everybody. Peter is my name. I'm working for MetaFacts. Yesterday, you have seen my colleague Russell already entertaining you a little bit. Today, I will try to level up a little bit at the intellectual level, but maybe not reach the level of some of the talks that we have seen so far. I would like to share some experience and lessons learned that we made when we have built a product that combines symbolic AI, knowledge graphs, and large language models. And one of the main things, or the objective that we try to achieve here, is to work on trusted knowledge identification. When using large language models, we know they do not always tell us the truth. So this trust thing is an important one, and I will come back during my talk in a couple of minutes. One slide on our company. We are a company of around 50 people. I would say the large majority is knowledge graph and semantic web geeks. And me personally, probably I'm not so long in this company, so not belonging really to this group, but happy today to share how we build together with our mother company, Digital Science, where we have access to scientific data, and MetaFactory, the software platform that we have created over the last 10 years, together to make a research project possible that we call the Dimensions Knowledge Graph. The main challenge that it addresses is for drug developers. They are facing the situation that every day thousands of new papers appear that could include important information. We have seen already there are so many data sets in the world and accessible that to get an overview of what's known is really difficult for these people. And so how we can make that easy? And this is basically the objective of the whole thing. What we have created is, and this is a commercial product, yes, but it's built on fair data principles, at least, so that we can say we have created a massive RDF knowledge graph that integrates data from public sources, but also data from the scientific publication fund that we have available. And we have integrated this in one mega graph, which is 33 billion statements, where we have metadata from publications, patents, grants, clinical trials. We have extracted researcher profiles, organization profiles. We have, and this will be the main focus now, also identified unique biological relationships in the text, 38 million so far. We have entity recognition applied on all these texts, put it all into somehow the graph, and in total, we have also up to 70 public data sets ready for integration. So at the end of the day, this allows a researcher to do a gap analysis. What is it that I find for my specific question in, for example, open targets? And what may be hidden still in literature that did not find its way into open targets? And this gap analysis is basically, it will end with my last slide when I show you how that works. But to keep the tension high, I would now explain how we did that, how we did this relationship identification for drug developers. These people are, for example, mainly interested in the relationships between genes, proteins, diseases, substances, including drugs, and how they are somehow associated with each other. And we have built, let's say, or educated a system that is able to distinguish more than 200 different relationships. How does it look like? If you look at a sentence from a scientific publication, and especially in the medical space, these authors have a lot of creativity writing very complicated sentences. And what you need to do is you need to transform the information in this sentence into a structured way that you can then upload it into a knowledge graph. And this is basically what we have done. You see here on the left side, a protein, then the relationship, the predicate, and then an object, in this case, again, proteins, and different type of relationships are identified here. How we did this in a practical process is that we started with scientific publications, where we used symbolic AI ontologies to identify the entities like proteins and so on, because this is an exercise where language model is not so good. So if you have really the demand for high quality identification of entities, still the ontology was very useful. But understanding the relationship between the two entities, how do they interact, how are they associated? This is where a language model cannot be beaten. In all our experience. And at the end, we put it all into what we call the dimensions knowledge graph, a system that is powered by the MetaFact software. So this was achieved basically by training a large language model, how to understand the different biological processes. And we have here these 11 biological processes. And what we have taught the system to do is to distinguish the author language. Is it a bold statement, or is it a maybe statement, a more blurry statement? And for example, activity, you can say, is the protein increasing the activity of another one, or is it just modulating, or even somehow related or potentially related? That makes a difference in the language. And this is something that we have been able to teach the system to recognize at a very, very good level, with the impact that the bold statements, the things that you are interested, if you want to, let's say, from millions of documents, want to find the nugget information, you want to have this bold information. So this is why we have created this matrix of relationship types. Here we see results, and one measure, and at the beginning I said working with a language model can be difficult because it doesn't always tell us the truth. And so one measure of the quality in this area is to look at the contradictions. That means if you have, like here, a message that you find insulin is increasing the activity of protein kinase B, and we find 1,241 scientific publications confirming this. What you measure is the contradiction. How many papers do we find where the author says there's an increasing effect? How many papers do we find where the author says the opposite, a decreasing effect? This level of contradiction gives us a measure how good is the language model when identifying this type of relationship. And you can see here, overall and over the all database, we have a 3% level of contradictions, which is, for us, amazing result. And you can see here also some examples. And if you look at the lower part, you can see also that we find a lot of documents, 796, where the language model has identified modulates activity of. This is a more, not so clearly defined, is it up or down, and even relates to, we find a lot of examples. So this is how we get this level of contradictions really to a very, very low level. But still, we are used to measure precision and recall. And this is, again, a more challenging thing, because if you want to distinguish between is potentially increasing or potential biomarker versus a biomarker, then even humans can discuss a lot about how to interpret sentences. And this is what we found when we created this data set, because we overall have put together a set of 1,400 test sentences and training sentences. So we had 2 humans reading these sentences and categorized them. And initially they had an agreement rate only of 60%. Means even humans can have very different opinions on how to interpret a sentence in this scientific environment. Over time, they learned how to work with it and achieved a level of 80%. Now, versus this test set, we have achieved precision of 70 to 80%. Also, the language model, if you run it 2 times, you get different results. So this percentage can vary. But here we can say, in terms of precision, also confirmed by further human validation by other people, the 80% is something that can be achieved. But at the same time, the recall, I have to say, here humans are still better. So overall, this is leading to an enormously rich set of information which can be used for many different use cases. From expansion of indications, that means you have a drug, you would like to know, are there any other diseases where it can be useful, drug target, candidate identification, potential new biomarkers, protein-protein interactions, and adverse events prediction are use cases that are all very relevant for these people. And we think with this combination of language model and symbolic AI, we're able to come up with really great results. Here, one example of how that looks like for expansion of indication. The competency question that we can answer here is which other diseases are frequently discussed in literature as being treatable with an existing medication. And what you see on the right-hand side is basically the list of references and the documents and the links to the publisher page where you can find these references, and also the sentence that gives us the reason why this document has been selected. And it's really impressive because in many cases, this description and this sentence is really only implicitly describing this could be a biomarker. Yeah, so I think here we found out earlier days we worked with pattern matching for relationship extraction, but this is a completely different game. So you can see I'm very impressed about our product, and I think it's really a very useful methodology that can also be applied in many other areas. I hope it's an inspiration for all those who work on the academic world that to learn from the experience that we have. We're happy to share. And also I'm available at the booth where a live demo is possible. Thank you for your attention.
Thank you for the talk. About the relation extraction part, you said you're using large language model. Are you using them in a prompt-based manner, like with prompt, or are you fine-tuning them and exploiting, I don't know, maybe some annotation and stuff?
It's a combination. So they get a prompt to say, this is how the relationship is defined, and then example sentences as training.
So you're not fine-tuning the large language models?
Not that I know.
Okay, thanks.
Hi. You were explaining that you're using literature data so human already interpreted data for your representation. I'm wondering how far can you go to the raw data, to the real data that was measured, and which is much more reliable than any human interpreted data. So how far can you go back to real sources of data and then use that to build these graphs? So instead of using literature, which is vague to my impression.
I think in principle, this is something that is a much easier task to do if you have the data already in a structured way. The challenge or the objective here, as you might remember, it was to compare what do I have in a structured database and what is maybe hidden in the text. And so to find this gap is something that is here also the objective. And maybe I missed this one, but if you look at this drug target candidate, for example, we have added here also a column where you see open targets scores, and even here you can find we have here an unknown relationship where it's not listed, this relationship in open targets, but we find 52 documents that give us an indication there we might have a drug target that has not been found in structured databases. But yes, sure, we intend to merge as much as possible into the graph so that also this structured data can be used by just combining them.
Yeah, got one quick question. So on the protein-protein interaction extraction, how is it just from the text, or do you somehow extract things from tables, supplementary materials? Because in my experience, having curated into Intact for many years, most of the real interaction data was not in the text. It was just the highlights that were given in there. And a lot of it was spurious because we did this exercise pre-LLMs with classic NLP, NER, and we got sort of to the 70-80% of, yes, there's an interaction in that paper, but the precise pairs were still really difficult to extract.
If there's a sentence in the table, we will find a sentence. But if it's just tabular data, we are so far not considering this. The thing here is that we work with the scale. That means having millions of documents worked through, let the AI read it, have a good recall rate. This gives us, let's say, a higher probability to find the information, because we all know that science is repetitive. That means one information published once is going to be repeated a couple of times, and so the probability is increasing over time that we find this. But yes, there's a lot more that you can do with this information hidden in scientific texts that we are today doing. We focus just on the text.
Hello, thank you for the talk. Do you trust Do you trust all the sources in the same way?
We list the sources ranked by citations. Yeah, so we don't take, let's say, an impact factor, because I'm not sure if that's fair. So we try to come up with at least a ranking where we see the most cited publications.